Okay, here is independent anti-multiplication rule. On this part, we have these two events, E and F, and we're gonna see when we have independent and dependent. So when I have these two events, and these two were independent, what that means, there is no relation between these two, between E and F. In other words, probability of E doesn't affect probability of F. And vice versa. So probability of E doesn't affect probability of F, and also probability of F doesn't affect probability of E when there is no relation between these two events. Now what we have for dependent. Again, we have two events, E and F, and these two are dependent. Meaning that there is a relation between E and F. And also probability of E affects probability of F. And also probability of F affects probability of E. Okay, now example, determine whether the events E and F are independent or dependent. Part A, we have these two events E and F. The first one on top, speeding on the interstate, and here F is being pulled over by a police officer. So obviously these are, between these two we have relation. And speeding increases probability of being pulled over, so this part is dependent. Dependent, and reason is speeding increases probability of being pulled over. Next one, again we have two events. The first one, you gain weight, and this event, you eat fast food for dinner every night. Obviously this one also is dependent, because gaining weight depends on eating fast food, or maybe eating more than needed. So this is dependent. And see, you gain a high score on a stat exam. Next one, Boston Red Sox win a baseball game. So these two, obviously there is no relation between these two. It doesn't matter if they win, how that will affect your score on stat exam. So this is independent. Again, in part A, we had relation between these two events. Part B, we had again relation between E and F. But C, there is no relation between E and F. That's why we have independent. Next one, use the multiplication rule for independent events. Okay, suppose that you flip a fair coin twice. What is the probability that you obtain a head on both flips? That is a head on the first, so head on the first, and you obtain a head on the second. So here is sample space. Okay, so this part is sample space of flipping a coin twice. On the first try, I can have, let's say, I had head. Second try, I had head. This is another one. On first try, head. Second try, tail. Another one, I can have on the first try, tail, and second one, head. Or maybe we got both of these tail. What we need on this part is, what is the probability that you obtain both of these heads? So we need this one. Head on both. So finding probability of So here probability of having both of these head is equal to, in total we have 4 outcomes, and on top how many we have both head. So we only have one, and that is on top. So that is the answer for probability of having both head is 1/4. Now next part is multiplication rule for independent events. So this is what we have for this part. Probability of E and F is equal to probability of E multiplied by F. We're gonna cover dependent events later, but write that part here too, so you can compare what is the difference. So for dependent event, we have probability of E and F, that is equal to probability of E multiplied by probability of A and probability of F depending on E. Now I want to use this one here on this part. So this was using sample space. Now I want to use this rule. So probability of, using that one or this one, probability of having head and second try again head. That is equal to probability of head multiplied by probability of head. So for when you're trying to flip coins, you have two possibilities. One is tail, the other one is head. We had this part before, so we transfer each one as 1 out of 2. That's why here probability of head is 1/2. So the chance for each one is 1 out of 2 because we have 2 possibilities here. And the answer again is 1/4. Example, what is probability of obtaining 5 heads? So here we have 5 heads in a row. Exactly same as what I did on the previous part, probability of head, and now I have 5 heads. So we have 1, 2, 3, 4. We have 5 heads. That is equal to multiply each one. Okay. As I said on the previous page, when you have coin, you have 2 possibilities. One is tail, the other one is head. So, and the chance for each one is 1 out of 2. Here we have 1/2 multiplied by 1/2. So for all of these, we have this probability. You can write that way, or you can write 1/2 to the 5th power. That is 1 to the 5th power is 1, 2 to the 5th power is 32. This is fraction. Now this one is 0.03125. So that is the answer. As for probability, we usually write in decimal number. Number 3 plays in sports are said to have hot streaks and cold streaks. For example, a batter in baseball might be considered to be in a slump or cold streak if he has made, okay, this is 10 out and 10 consecutive bats. Suppose that the hitter successfully reaches base 30% of the time he comes to the plate, run to 4 decimal places. Okay, part A, find and interpret the probability. The probability that the hitter makes 10 outs in 10 consecutive at-bats, assuming that at-bats are independent events. So I'm going to find the probability. I'm not working on that part. So find the probability that hitter makes 10 outs in 10 consecutives. Now what we have here is, since I have 30%, that is success. Now we have, and here it's asking for failure, so we have outs, but that is successfully reaches base 30%. What that means, for this part we have 70% chance of out. How we got that? This is 1 minus 30% that we have here. So that is 70%. So success was 30%, and based on that, failure is 70%, or failure, or here in this case we used out. Now finding the probability of, here we have 10 outs. I'm using 3 dots, so I have 1, 2, up to 10. Okay, that is equal to out multiplied by out So here probability of out is, this one is 70% chance of out. Or I can write the 70% to the power 10, because we have 10 out. So that is equal to 0.02825. And it's asking to round to 4 decimal places. So this is 0.0283. Okay, so that is the final answer for part A. Now part B, are code streaks unusual? Remember, for unusual, you should compare if that probability is less than 5%. If so, you're gonna have unusual. So based on what we got on part A, that one, we have 0.0283. And we want to see if this one is less than 5%. Yes, this is obviously less than 5%. And the answer for this part is yes, unusual. Part C, find the probability here makes 5 consecutive outs, and then we just base safely. So first he had 5 outs, so 5 failure, and after that finally he got that one base, so meaning that we have 5 failure and 1 success. So the first try was out, second out, third out, fourth out. Here's 5. 5 is out, and finally after that we have base. So finding the probability for that part, multiply each one. So we have 5 out and 1 base. Now probability for out was 70% and for base was given as 30%. Adding out and base, 70% plus 30%, you should have 1, so there's 100%. Okay, so that is equal to, multiply all these numbers, it's 0.050421, and we should round it, that is 0.0504. So this is the answer for part C. Now next part, compute at least probabilities. So here we have at least, and what that is, when we have at least, meaning that we have greater than or equal to. Now example, compute the probability that at least, so here we have at least one male out of 1,000 aged 24 years will die during the course of the year. If the probability that the randomly selected 24-year-old male survives the year is 0.99886. So what we have here is probability of survive, is that one. And here it's asking to find the probability of at least one die. Okay, so here we have randomly selected, meaning that I have, so it's randomly selected, we have independent events. What it's asking to find us. So since it's asking at least one male die, what that means, we can have one die or two, because that is at least one or more. Or 1,000. But this is one die, two die, or 1,000 die. To find the answer for that part, since we have or in between, that means we should use addition. So when you have or, addition, when you have and, multiplication. So this is what they ask you to find. And what we don't have here is here we don't have only none is not here. What I have here is probability of survive is that one. I don't have probability of dying. So that's why I want to work based on that. But this is what they're asking. But instead of this, we can write what I'm writing here. Because usually for at least, you should follow this. So that is what it's asking. But here, I'm using at least to show that how we can get the answer. So probability of at least one will die. That is equal to 1 minus, so you should subtract whenever you have at least. Subtract probability from 1. So at least 1 will die. Now here we have probability of the first one survive and second one survive and here we have 1000. Okay, so that is equal to 1 minus probability of first one here survive in between and, so we have multiplication. Multiply so here we have multiplication, and I can use power instead. So probability of survival is that number we have 0.9986, and how many times we should multiply this one is 1000. That's why I'm using power on top, and that is equal to 1 minus 0.2464, and the answer is 0.7536. So this is the probability of at least one will die. Okay, now example number 5. So here is test to determine whether the HIV antibody is present. The test is 99.5% effective, which means that the test will come back negative if the HIV antibody is not present 99.5% of the time. The probability of a test coming back positive when the antibody is not present, a false positive, so this is false positive, is 0.005. Suppose that the result is given to 5 randomly selected people who do not have the HIV antibody. So this is who do not have HIV antibody. Part A, what is the probability that the ELISA comes back negative? So here is negative for all 5 people. So what is given? We have this one, false positive, and we have come back negative if the HIV antibody is not present, is this one. I'm writing it up over here. Probability of negative is running in this one number 0.995, and positive is that one is 0.005. Now here we have negative for all 5. So all 5 negative. I have the first one negative, second negative, third negative. So all of these 5 negative. In between we have the probability of, okay, the first one negative. Okay, let's write that this way so you can see what I'm doing here. Here, what that means, we have probability of negative and negative. So we have 1, 2, 3, 4, 5. Since we have and in between, we should multiply. That is equal to, probability of negative is 0.995 multiplied by, again, probability of negative 995. So that is equal to, instead we can write this way, use power. And rounding is 0.9752. So that was the answer for part A. Now part B, what is the probability that the ELISA comes back positive for at least, so here we have at least one of the 5 people. Since I have at least, I should write 1 minus. P, probability of at least 1, here is positive. That is equal to at least 1 positive. I should write 1 minus probability of all 5 negative. See, I don't want to have negative. That's why I should subtract that from 1 to get the answer for at least 1 positive. So here we have positive. Here on this part I have negative, all of them. So probability of all 5 negative. Or in other words, what that means here is 1 minus probability of none is positive. See, none is positive. It's exactly the same as having all 5 negative. And when you have none positive, you should subtract that from 1 to have at least 1 positive here on this part. The answer is, we already have the answer for all negative from previous part is 0.9752. And that is 0.0248 and rounding it. It didn't ask us to F. We should round it, but I'm rounding. Okay, number 6, according to the Department of Health and Human Services, 30% of 18 to 25-year-olds have some form of mental illness. So we have 30%. What is the probability to randomly select 18 to 25-year-olds have some form of mental illness? What is given here is probability of having some form of mental illness, that is 30%. So based on that, probability of no illness is equal to 1 minus probability of mental illness, which is 30%, so that is equal to 70%. Part A, so we should find probability of that part, mental illness, and we have two randomly selected. Again, we have independent events. And instead of writing mental illness, I'm writing mental. Mental and mental. That is equal to, we have 30%. So you should multiply 30% multiplied by 30%. That is 30% to the second power. So it's 0.09. Now next part, what is probability 6 randomly selected have some form of mental illness. So again, exactly same as that, but now instead of having power 2, here we have 6, because that one was 2 randomly selected. Here is 6 randomly selected. Instead of writing mental and mental and mental, having all 6 here, I'm writing 6 mental illness. Again, since we have randomly selected, these are independent, and that is equal to, for each one we have 30%. Since I have 6, use power 6, or you can multiply 30% multiplied by 30%, so all of these. The answer is 0.000729. Now next one, what is probability at least? Now we have at least one of 6 randomly selected has some form of mental illness. We have 6. So at least one of 6 has some form of mental illness. That is equal to, again, we should subtract 1 minus. So 1 minus probability of none of 6 have mental illness. So no illness is 70% based on this part. Multiply this by itself 6 times. Or use power. That is 0.882. Part D, would it be unusual that among 4 randomly selected, none has some form of mental illness? So we have 4 and here is none. And it's asking if that one is unusual. So we have 4 and it's none, already none. So here we have 1, 2, 3, 4. That is equal to, we have none has some form of mental illness. So no illness, we have 70%. 0.7. So this multiplied by itself 4 times. The answer is 0.2401. And now compare that number with 5%. This was rule when you want to find out if your events are unusual or not. So if that probability is unusual or not, you should compare it 5%. Obviously, this number is not less than 5%, meaning that this is not unusual. Next one, for the parallel structure of identical components, the system can succeed if at least one of the components succeed. So we have at least one of the components. Assume that components fail independently of each other, and that each component has 0.15 probability of failure. So what is given is probability of failing is 0.15, and based on that, probability of success is equal to 1 minus probability of fail. That's 1 minus 0.15, and it's 0.85. Part A, would it be unusual to observe one component fail? 2 components. So the first one is one component. Finding the probability of fail. We already have that one is 0.15. It's asking if this one is unusual. Compare this with 5%. So this is not less than 5%, meaning that this is not unusual. Now the next one, trying for 2 components. Probability of fail and fail. So this is probability of fail multiplied by probability of fail. We have 0.15 power 2, that is 0.0225. So this one is, this number is less than 5%. The answer for this part is yes. This is unusual. Part B, what is probability that the parallel structure with two identical components will succeed? That is equal to 1 minus probability of both fail. We already have the answer from that part. It's 0.0225. That is equal to 0.9775. This may be confusing what I use at least once succeed, because here we have what is probability that a parallel structure with two identical, so we have two identical components will succeed. I'm going to explain that one more. So let's write that part here. So this is for part B. What possibility we have? The first one, I can have success, second fail, or fail, success, or success. Why I don't have fail? Because here we have two identical components will succeed. We only have succeed, we don't have failure. So I should have at least one succeed. See, here I have success, but here we have two success. So we have 3 here. And now finding based on what we have here, this is sample space. Now probability of at least one success, that is equal to probability of, writing that way, success fail, or probability of fail success. This one is harder to find the answer. So probability, here we have, okay, let's use comma in between. And that comma means I used and in between. When you have and in between, you should multiply. So here is actually, this is probability of success, and so we should multiply by probability of fail. Here is or, add probability of fail, multiply by probability of success. Here is or, so you should add. Here same thing, probability of success, multiply by probability of success. That is equal to probability of success was given was 0.85, and fail is 0.15 plus here fail is 0.15, 0.85. 0.85 multiplied by 0.85. So here we have 0.1275 plus, same thing here, plus 0.7225. So add all these, the answer is 0.9775. So we got exactly the same answer. But we have more steps here on the spot. So use that one or this one. Obviously, this is harder to find. Now part C, how many components would be needed in the structure so that the probability that the system will succeed is greater than 0.9999. So on this part we should guess and check that how many components we should have. And the probability of, I don't know how many components we should have to have this probability equal to 0.9999 or more. So starting here with 2 components. So we already know the answer for that part. Here is 2 identical components will succeed. And here we have again succeed. So for 2 components succeed, we had 0.9775. We already know the answer from part B. The answer is 0.9775. And this is not enough because this is not equal to 0.9999. So this is not enough and we should continue. Now 3 components. So probability of succeed. That is equal to 1 minus probability of all fail. Since we have 3 components, now we have 1 minus 0.15 to the 3rd power. And that is 0.99663. Again, is not enough. Now 4. 4 components. Again, 1 minus probability of all fail. So it's 1 minus. For fail, we have 0.15. And all, since we have 4 components, power is 4. That is 0.99949. Again, is not enough. Now 5. So probability of success 1 minus probability of fail. So all fail is equal to 1 minus 0.15 to the fifth power, because we have 5 components. And that is 0.99992. Here we got that number is equal or is greater than or equal to. So this is what we need. So yes, this one is enough. And what that means, here on this part we need 5 components. To have this probability greater than or equal to 0.9999. Okay, and this where we have summary rules of probability. So we covered all these. Probability of each event should be between 0 and 1, and adding all of them should be equal to 1. And when you have or in between, so this is union, is probability of E plus probability of F minus probability of E and F, and is intersection. And complements, we had probability of complement of this event is equal to 1 minus probability of E. And the last one that we covered was probability independent for independent events. So probability of E and F is equal to probability of E multiplied by probability of F. Okay, so I finished this part.